In this problem, we have a bungee jumper preparing to leap off a bridge in New Zealand over a river. We're trying to figure out in this problem how long the unstretched cord would be. We're given the spring constant of the cord, the amount of force applied as it stretches each meter. You know the mass of the jumper, and again, we know the height that they are above the water. It's going to be really important anytime you're dealing with these problems. Hopefully you're realizing we're going to deal with energy, but it's important to draw a picture, right? So let's look at a scenario here. At the start, you have your jumper. All right, let's draw them here. And they're attached to a cord. Now, it's unstretched, right? It's just going to be hanging there, right? And it's attached to the base. And you probably got your water down here. Let's exaggerate a little bit. Here's our water down here. Now, let's call this position 1. Well, what kind of energy do we have at 1? Well, we know that from here to here, this is 40 meters all the way to the water. That's what's given in the problem. And we know this object, this person, has a mass of 60 kilograms. We also know that the spring constant K of the cord is 100 newtons per meter, right? That's not going to change. But that's where he is at the top. Does he have energy? Well, he certainly does, right? He's elevated. Is he moving? No. Is he stretching or compressing that bungee cord? No. Right? So we can say at position 1, we are all GPE. Well, later he's going to jump, right? And as he jumps, that cord is going to come down. It's going to get to a point where it is not yet stretched, but fully extended, right? And so at this point, let's call this position 2. And at this point, it might help to label the length of the rope. Let's call that L. That's going to be the length of the bungee cord. Turns out L is what you ultimately want as an answer for this problem. How long is the unstretched cord? All right, so this cord is just hanging. He hasn't actually been, it's not pulling on him yet, but right at this instant, he's going to start feeling the pull of that cord. Well, what kind of energy do we have at position 2? Well, if we're calling GPE at position 1, it's elevated. Well, we need to identify again. Let's say that the height at the water is 0 meters. Well, then he's still elevated, right? So we have some GPE at position 2, but he's also now moving. We have kinetic energy, right? This guy's going to have some velocity downward. Well, what happens if he, in this problem, gets just to the water's surface, right? The minimal speed at impact, meaning he's just kissing the water at the end. Well, let's look at that, right? In this case, he would have that cord is fully stretched, and he's just kissing the water at the bottom, right? And we know if he's at minimal speed, well, let's set the velocity at position 3. V3 is equal to 0 meters per second, which means, well, what kind of energy do we have at position 3? Well, they're now at the water at a height of 0. There's no GPE. They have no velocity. They're not moving, so no KE, but they're certainly stretching that bungee cord, right? So at this point, we have elastic potential energy. And if we're trying to solve with energy, we know that we can say that the energy at 1 is equal to the energy at 2 and the energy at 3. And if we know the energy somewhere, it's got to be the same amount. Well, what is the length right here, by the way? Well, if from here to here, if the length of the unstretched length is this, well, then this remaining distance would be x, the stretch of the spring, or of the rope. All right, so when we're solving now with energy, let's look at how we would set this up. We can say that the energy at position 1 is equal to the energy at position 2, and it's also equal to the energy at position 3. What's nice is we don't care about the path. We could figure out the velocity at position 2 if I want, and then go from 2 to 3, but we can bypass that middle position and just set those equal to each other. The energy at 1 is equal to the energy at 3. And what kind of energy is at 1? Well, we have GPE at position 1, and at position 3 we have EPE at position 3. And our equation for GPE is mgh at 3, and EP is 1/2 kx squared. And if we know x and we know the height of the jump, we should be able to figure out the unstretched cord, right? So let's plug in the values. We know the jumper is 60 kilograms. Gravity is 9.8, and the height is 40. we can calculate the total energy this jumper has. 60 times 9.8 times 40. The total energy is 23,520 joules. 23,520 joules is the total energy this jumper has just by being elevated. And on the right side, we have 1/2 of 100 times x squared. So that's going to be equal to 50 x squared. And let's solve for that stretch. All right, the stretch, if we divide by 50 on both sides, we can take that value, divide by 50. We get 470.4. 470.4 is equal to x squared, but we're solving for x, so we're going to take the square root of both sides. And in doing so, we figure out how far it stretches. 21.69 x is equal to 21.69 meters. All right, well, what does that mean? Well, that's actually not our answer, right? We want L, right? Well, how do we find L? Well, we now know that x, this distance, is equal to 29.67 meters. Well, what does L have to be? Well, again, when you draw the picture, it makes it really clear. If the total height is 40, then L must be 40 minus that 29, right? We know that the length of the unstretched cord plus its stretch has to be exactly 40 meters, right? That would get us all the way to the bottom. And so L plus 21.69 meters has to be 40, which means the length of the unstretched cord would be 40 minus that answer. And I get 18.31. 18.31 meters is the unstretched cord length. All right, so if I'm hooking up a cord to this jumper, I know that if I hook him up to an 18-meter cord, he's going to fall as far as possible and just kiss that water at the bottom. Again, hopefully you see how valuable drawing the picture is in creating this new variable L, the length of the cord I want, and understanding that with energy we can skip that middle step. We certainly could have figured out the velocity at 2 if we wanted it and use that velocity to find that same stretch. But we can bypass that and go right from position 1 to position 3 and find the length of that unstretched cord.